Alright, so this is going to be section 6.3, cylindrical shell, or the shell method for short, the way to do it. Okay, so this is going to be the last technique to be find the volumes with a solid, and usually this is the most difficult of the three bones. The disc being the easiest one, the washer being normal size. Is the hardest one of them. For me, it is when it comes to it. So when it comes to the shell method or the cylindrical method, when it comes to it, is in most cases we're going to be using this when it's very, very hard or almost impossible to solve for the variable itself. Okay, so solve like for x, okay, or for y, when it comes to it, when we're doing these revolutions around those portions. Okay, so for example, the concept of what this method is all about is, let's suppose we have, like, this is a curve here. And let's suppose like y is some crazy, outrageous one. Something like that. Okay. And notice, right, let's suppose we want to take it and then rotate it around, let's say, the y-axis. So we're going this way, right? So if we do our washer method or a shell method, a washer or a disc method, since we're rotating this way, doing perpendicular to it, and that's going to be almost impossible, right? So therefore, we're bounded between the y-axis, and therefore we have to take this and integrate it with respect to y. But good luck trying to solve for x there, right? It's almost almost impossible to solve for x unless you have a computer or something like that. So for things like this, how do we actually solve for the volume given this portion here? And that's where this induction to the shell method comes into play. Okay, so the whole concept of the shell method is, well, now if I just rechange it, so again, going across this way, but now what we have a line here, and we rotate it this way instead of doing perpendicular to it, we actually get something called a cylinder. So again, just rotate this all the way around, or like a soda can. So you get something like this. Here again, it's pretty much a hole in the middle, right, at both ends. Because again, we rotate it this way, so we just get a little thickness of it. So the thickness there. Okay. So the concept of this is, well, how do we solve for this one? Or how do we find the area of this, and then going back over here and just take the sum of all of them, right? So in other words, take the integral of it. So remember, when it comes to volume, right? So total volume is going to be the same process we did earlier, right? When it came to the washer, we're going to find, the volume of the entire thing, and subtract the volume of what we don't want. Okay? So essentially, this is the volume of the outside minus the volume of the inside. So in this case, it has a height of h, depending on what we want. And this portion here, or this change, is called delta r, or the change of the radius, right, when it comes to it. So basically, a bunch of math, right? So if you guys don't remember, volume of a cylinder is 2 pi r/h. So if we just subtract the portions and do it some, again, a little bit of algebra when it comes to it, we get this at the end. So the volume after some algebra is equal to 2 pi r/h times delta r, which is a change of r. Okay? And this is pretty nice because the circumference is exactly 2 pi r. H is considered the height, as we know, and delta r is considered the thickness of the cylinder itself. So each one represents one thing when it comes to it. Okay? So therefore, we have our new definition of the shell method. So the volume of the solid obtained by rotating about the y-axis, the region under the curve y equals f of x from a to b, is the integral from a to b of 2 pi x times f of x dx. Where again, this is the circumference, this is the height, and this is the thickness. Okay. So all that comes into play. And again, the only thing we got to be careful of is the radius. So, that radius can be the same thing, the same process how to find it as the washer method itself, and also the disc method. So just be very worried about that. You just don't plug in x and just call it a day. You still have to identify that portion is there. And you'll see that in a little bit when we do that. Okay. So let's try an example. So let's find the volume of the solid that is obtained by rotating about the y-axis the region bounded by y equals x minus x to the fourth and y equals 0. So just like everything else, let's figure out what's actually happening here. Okay. So let's just graph this a little bit, right? So when we plug in 0 into here for x, we get 0 out for y. Okay. If we plug in 1, so 1 minus 1 is 0. Okay, so somewhere in between here, it goes this way. So let's suppose it does something like that. And we can graph it perfectly, but we don't care too much when it comes to it. Okay. All right, so we have that portion. So we kind of have a bounds of integration because we want y equals 0 to be bounded by. So y equals 0 is the actual x-axis. So essentially this is going to be our region we're going to be rotating. And we're rotating about the y-axis, so we're going to be rotating this way. So kind of like our picture of our example before. So therefore, if we use the shell method, our thickness is going to be there, and we're rotating this way. Okay. So if we do this now, according to our equation, it's going to be the integral of a to b, so from 0 to 1, okay, of 2 pi, and x, remember, is the radius of it. So the radius is from here to here, and that's always going to be x itself, in this case. And then times our function of x minus x to the fourth, and dx. So we can go simplify this a little. We can bring this x in and take this out, so we can have 2 pi times the integral from 1 to 1, or 0 to 1, and plugging this in, it gives us x squared minus x to the fifth dx, which makes it easier just to look at. All right, so integrating this gives x to the third over 3 minus x to the sixth over 6. Evaluate it. Evaluate it from 0 to 1 times 2 pi.